Hi, everyone. I'm not going to have you work on work, this physics principle. It's optional in my class. But here's the idea. The work W applied on an object, let's say a brick that you're trying to move along the floor, all right? And let's say that the work applied, you're interested in the work applied on this brick, okay, by a constant force F. So you're pushing it with a constant force, okay, as the object moves along the displacement vector D. Okay, so you want to move the brick from here to here, basically. That's the displacement vector. Now, if you're dealing with a one-dimensional picture where everything's pointing in the same direction, it's a one-dimensional picture, right? Then basically work equals force times distance, just as scalars, right? Work equals force times distance. But now what happens if you're on an incline, right? I should say here, even if you're on an incline, as long as the force vector and the displacement vector are pointing in the same direction, well, the work applied is still the magnitude of the force vector times the distance traveled, okay, the length of this displacement vector. Basically, work equals force times distance, but since we're on an incline, we're talking about the magnitude of F times the magnitude of D. These are vectors. Before, we could get away with treating these as scalars in the one-dimensional case. Here, we have to talk about lengths of vectors. All right, but here's where it gets really interesting. What if there's a helicopter pulling on the object and there's actually a non-zero angle between these two vectors? Here's the interesting case. Then what's the deal with the work applied? Well, the thing is, so if this is the force applied by this helicopter, that's denoted by the length or magnitude of F. The thing is, we care about the aspect of this force in the direction that we're interested in, the direction of the displacement vector. We want to know what the deal is, the impact of work as this object is moved up the incline in this direction. So we care about the aspect of force in this direction. So instead of this vector, we want to look more at the projection vector over here, which is sometimes denoted as proj, the projection vector. And the component here is the signed length of the projection vector. If the helicopter is working against you, the component will be negative, actually. Right. But here, the helicopter is helping you as you drag the object up this incline. It's going in the same general direction as this displacement vector, generally. So basically, what we want to know the signed length of this projection vector over here. If you project the F vector on the D vector, the notation is this. Okay, that vector I'm talking about, the projection, the projection of, I keep doing that, the projection of F along D. That's this vector over here, in purple actually, that's this vector. The signed length is called the component of F along D. That's the aspect of the force vector we care about in this direction. Well, what's the relationship between this angle, this adjacent side, and this hypotenuse? That sounds like SOHCAHTOA, cosine. It's a cosine relationship. This is given by the hypotenuse times, basically r, cosine of theta. Put this all together, and hey, the product of lengths times the cosine of theta. If you finagle this formula over here, right, cosine of theta is the dot product or the product of the lengths. If you solve this for the dot product, you have a geometric definition for dot product. Before, with the algebraic definition, we said that V dot W was V1 W1 plus V2 W2, algebraic. But now geometrically, we can say that the dot product is the product of the lengths times the cosine of the angle between them. That's another way of defining a dot product, even in the absence of a coordinate system, really. Okay, so basically, all this, right, work equals the relevant aspect of force, that magnitude, times the distance traveled. It ends up being the dot product. Work is given by the dot product. So that's a key application in physics.